On a beautiful summer evening back in 1996, just a few minutes after sunset off the coast of Long Island, something unthinkable happened on board this Boeing 747 as it was climbing towards its cruise altitude. This would eventually go on to become one of the most studied, analyzed and debated aviation incidents in modern history, and also produce one of the most exhaustive investigation reports ever written. And yet, despite the depth of that investigation and the sheer volume of physical evidence examined, it would still remain an event surrounded by misunderstandings, incomplete explanations, and persistent misinformation. And that is why we have now decided to tell you this story. You see, the story of Transworld Airlines Flight 800 was not just an initial mystery, it would also create a kind of turning point. One that forced the aviation industry to finally reconsider long-standing assumptions about the way planes were both designed and operated. But to really understand why that was the case, we have to start long before anything actually went wrong. In the early afternoon of July 17, 1996, the Boeing 747 involved in this story was completing an otherwise routine transatlantic flight from Athens, Greece, and was now descending down towards John F. Kennedy International Airport in New York. The whole flight had proceeded without any issues at all, with no mechanical snags or major technical faults of any kind. Back in Greece, fuel had been uploaded in all of the aircraft's fuel tanks to cover the journey, but since the center fuel tank is always used first, it was by this time empty. Well, almost anyway. In any case, the flight crew soon landed at JFK without issue and then taxied the aircraft into the gate. And once there, the passengers were disembarked and the turnaround process ensued, with the aircraft soon being set up for its next flight, back over the Atlantic towards Paris-Charles de Gaulle Airport in France. The crew that had been operating from Greece left the aircraft and was replaced by the next crew, who was headed up by a 57-year-old captain. He had approximately 18,700 hours of total experience, including over 5,500 hours on the Boeing 747, and he was accompanied in the right seat by a Czech captain, aged 63, who had 17,200 total hours, of which more than 4,700 hours had been logged on the 747. The flight engineer stations would be occupied by a trainee and an instructor, whose combined flight experience exceeded 19,000 total hours, so this would be a very experienced crew to say the least. In the back, they were joined by 212 passengers and 14 cabin crew members, making this coming flight a little over half full. Now, as part of this turnaround, the aircraft was, as always, at the center of a carefully coordinated sequence of activity. Baggage containers were exchanged beneath the fuselage, catering services replenished the cabin, fueling operations were on the way, and maintenance personnel carried out the inspections and servicing actions that were required. And as all of that work went along, nothing stood out as different from the thousands of other turnarounds that this aircraft had done in its career up until this point. It in itself was a beautiful red and white Boeing 747-131, registered as November 93119, which had been delivered brand new to Transworld Airlines back in November of 1971. By the summer of 1996, it had accumulated approximately 93,000 flight hours, with more than 16,000 pressurization cycles, figures reflecting a long and busy service life. Now, although it had been delivered nearly 25 years earlier, it is important to understand that in commercial aviation, age alone doesn't really work as a meaningful indicator of safety. Large transport category airplanes are designed to withstand decades of continuous operation as long as they are maintained properly. And by the mid-1990s, the industry had already undergone a profound shift in how aging fleets were monitored, inspected and maintained. That shift had been accelerated in the wake of accidents such as the Aloha Airlines Flight 243 fuselage failure, which was an event that had fundamentally changed regulatory thinking by highlighting that structural fatigue and environmental exposure could accumulate in ways that had not yet been fully captured by traditional maintenance assumptions at the time. So as a result, this 747 was now being maintained according to the latest continuing airworthiness program, designed to ensure that, as it got older, it still remained just as airworthy and safe as the day that it was delivered. But while structural elements whose failure modes are measurable and extensively studied were now given more critical attention, not all aging systems were yet treated equally, which is worth keeping in mind. Anyway, as preparations continued for the coming departure towards Paris, the pilots and fuelers soon coordinated a fuel uplift in accordance with the operational flight plan that we're going to use. Now, New York to Paris was well within this Boeing 747's range capabilities, and with the aircraft only being about half full, there was no reason to fill up all available tanks on this particular leg. Carrying excess fuel would just mean unnecessary weight, which in turn would increase the fuel burn. So instead, all of the required fuel for the Atlantic crossing was loaded into the 747's wing tanks. And that also meant that the center wing tank, which was located within the wing box section beneath the fuselage, was largely empty. But the term empty in this case was a little bit misleading. You see, although no usable fuel was loaded into it, approximately 135 kilos of residual fuel was still left in the tank from the previous flight, which was equivalent to roughly 170 liters. But because the center tank's total capacity was nearly 50,000 liters, this amounted to less than 0.5% of its volume and was too little to actually be reached by the fuel pumps, so it was operationally unusable. Now, the central tank in itself is a large structural cavity integrated into the aircraft's wing center section, making up almost the volume of the entire wing box, and with an internal volume of about 48 cubic meters. So spread across the floor of that tank, those residual 170 liters would likely not even resemble a visible pool, but instead form a thin film and maybe some tiny puddles, collected unevenly along structural ribs, spars and low points within the tank. And from the cockpit, the tank would appear entirely empty. In any case, as the plane and its crew now sat at the gate preparing for the flight, they were met by a couple of small routine disruptions. First, the refueling operator came across an unexpected complication when the fuel tank's automatic volumetric shutoff valve, which is supposed to stop the fuel uplift when the tanks are full, triggered too early and therefore stopped the fuel uplift before the required fuel was on board. The fueler eventually fixed that by resetting the circuit breaker for the shutoff valve, which allowed him to complete the refueling manually. And although investigators would be unable to show if this event was related to what was about to happen, it could have been a hint of a larger issue lurking in the shadows. And when we're on the subject of dark things in the shadows, if you have noticed an uptick in phishing emails, spam text or robocalls lately, there's a very good chance that your personal information is right now being bought and sold online. You see, companies known as data brokers collect and trade details like your email, phone numbers and home address and even more than that, which incredibly is 100% legal. But the good news is that you can therefore also tell them to stop, even though that can be a time-intensive and really frustrating process. That's why I have left that in the hands of experts, like today's sponsor, Incogni. Incogni will do all the heavy lifting for you by finding all brokers, which can be a lot, and then file legal requests for those to remove your data from their systems. Now, trying to do that manually would take weeks, but with Incogni, the setup is super quick and straightforward. And once they're up and running, Incogni will then continue to work in the background for as long as you are subscribed, constantly scanning and protecting you. For me, that has meant way less spam and robocalls, which in turn means that I can concentrate on creating more videos like this one for you guys. And then Incogni also sends me updates every week showing me their progress, and you won't believe just how much work they've done so far. So if you want the same protection for your data, then scan this QR code or go to incogni.com/pilot and use the code PILOT at checkout. That will give you a whopping 60% off their annual plan, which is awesome. Thank you, Incogni. Now let's get back to the video. After that, while the fueling was still being finalized, TWA staff suddenly noticed that a bag had been loaded into the cargo hold without its owner being confirmed to be on board, which obviously had to be corrected for security reasons. This meant that the cargo hold now was reopened and the luggage identified and then removed, only later to be reloaded again when the cabin crew found out that its owner had in fact been on board the whole time. Now this is something that happens all the time, and it's yet another precaution that has been added by tragedy. In this case, the bombing of Pan Am Flight 103 over Lockerbie 8 years before this flight. Meanwhile, an airport service vehicle also broke down directly behind the airplane, which effectively blocked the aircraft from being pushed back. So the scheduled departure time soon came and went, with the passengers and crew just waiting for the ground crew to find a tow vehicle to get the broken down service car out of the way. Throughout this time, the airplane's auxiliary power unit in its tail continued to operate, supplying electrical power and bleed air to the aircraft and its air conditioning systems. The 747 has 3 air conditioning packs, and 2 of them, who were mounted beneath the wing center section, had been running continuously for hours to maintain the cabin comfort in the summer heat. Which kind of makes sense, since the outside temperature was sitting at around 27 degrees Celsius or 82 degrees Fahrenheit. Now, the packs themselves were designed to cool the cabin by extracting heat from the APU or engine bleed air before pumping it into the cabin. But that meant that they also had to discharge the excess heat somewhere, and in this case, some of it went straight into the aircraft's own structure. And like I mentioned before, on the Boeing 747-100, these 2 packs were located beneath the center wing section, and almost directly under the center wing tank, separated only by some structural elements, but almost with no thermal insulation. So this in turn meant that as those packs kept working, heat now migrated upwards, gradually warming the almost empty tank above. Which in turn meant that something was now happening inside the tank that wasn't visible to the crew nor anyone else. The little remaining fuel was now in contact with outside air from various different vents, and as the packs and the ambient temperature started heating it up, it started mixing more and more with the surrounding air, gradually increasing the concentration of jet fuel vapor within the tank. Now, fuel vapor behaves very differently from liquid fuel. In its liquid state, jet fuel is actually quite difficult to ignite. In fact, Jet A fuel at room temperature will put out a lit match as easy as water will. But when that same fuel is in a vapor state mixed with air and in the right concentration, it can become highly combustible and even explosive. The concentrations where that can happen are in a range that we refer to as the flammability envelope, and below that range the mixture is too lean to burn, and above it it's too rich, but in it the conditions are just right for combustion. So as this tank now warmed, the vapor concentration continued to increase, gradually moving the mixture towards that flammable range. But that was actually neither an unusual state or even unexpected. You see, at the time, it was already well understood that flammable vapor conditions often did exist within the fuel tanks of airliners. Later studies show that across all airliners globally, most fuel tanks contain vapors in the flammable range around 7% of the time, increasing to 30% of the time for center wing tanks located near air conditioning equipment. Because of that, flammable vapor in the tanks was not seen as an anomaly, but instead an inherent characteristic of conventional fuel tank designs, and something that just couldn't be avoided. So with that in mind, the aircraft designers had instead focused on eliminating potential ignition sources in and around the tanks. Now this was primarily done by minimizing electrical wiring inside of the tanks and by limiting the voltage of any essential wiring that had to be in there. And also by creating alternative paths for lightning strikes, as well as eliminating pathways that could allow fire to spread to the tank from nearby equipment like fuel pumps. But by 1996, the aviation world had already seen that this logic wasn't really foolproof. More than 3 decades earlier, Pan Am Flight 214, a Boeing 707, had crashed in Maryland after a lightning strike had managed to enter a vapor-filled fuel tank, triggering an explosion. And in another case, back in 1976, a Royal Iranian Air Force Boeing 747 had crashed near Madrid, again after lightning had entered a partially empty wing tank, causing an explosion that led to the structural failure of that wing. In total, the NTSB would later be able to identify 26 different cases of fuel tank explosions in transport category aircraft between the years of 1959 and 1996, with causes ranging from lightning strikes to bomb blasts, short circuits and other equipment malfunctions. But back on board TWA Flight 800, after 79 minutes of total delays, the various ground complications were now finally sorted. The disabled service vehicle had been towed away, leaving the area behind clear, so the aircraft was finally cleared to push back from its gate with all applicable checklists and procedures completed. The engines were then started in sequence, and after a relatively short taxi out to runway 22 right, at time 2019 local, the mighty Boeing 747 finally took off, basking in the glow of the setting sun. Following the departure, the aircraft then climbed steadily, whilst executing a standard left-hand turn associated with its departure routing along the coast of Long Island. As its climb continued, the pilots worked through their routine tasks as they always would. The engine performance was monitored, all normal system indications were verified, and the pilots stayed in close contact with air traffic control, who soon cleared them to continue the climb to an initial altitude of 13,000 feet. And it was after reaching 13,000 feet, around 10 minutes after takeoff, that the first subtle clue appeared that indicated that something was potentially wrong. The cockpit voice recorder now captured how the captain observed an unexpected fluctuation, causing him to say, "Look at that crazy fuel flow indicator there on number 4. You see that?" Now this remark referred to the fuel flow indication for engine number 4, the outboard engine on the right-hand wing. The fuel flow instruments measure the rate at which fuel is delivered to the engines, and under normal, stable thrust conditions, these typically show very smooth and predictable values. Now, minor fluctuations can occur for a variety of benign reasons and therefore aren't usually indicative of anything to worry about, unless they are accompanied by other strange engine indications as well. So initially, no one really responded to the captain's observation. Now, obviously there might well have been some non-verbal reactions that the cockpit voice recorder didn't capture, but we'll never really know for sure. In any case, nothing else on the flight deck at this point suggested that anything serious was going on. The remaining instruments continued to display stable, ordinary indications. So in that context, that fluctuating needle would have appeared far more likely to represent a minor sensor anomaly than the first hint of something bigger. But it was likely showing something bigger, something huge in fact, and also something that the pilots would have had no chance to do anything about. But the full significance of this tiny indication is really only understandable in hindsight, and only if you know a little bit more about the fuel indicating system on the Boeing 747-100. The Fuel Quantity Indicating System, or FQIS for short, measures the amount of fuel present within each fuel tank and then transmits that information back to the cockpit. It does that by using a system based on electrical capacitance, rather than something mechanical like a float, for example. Inside each tank, there are these long probes who act like tiny electrical sensors, and the readings from those change depending on whether they are surrounded by air or fuel. You see, jet fuel and air have very different electrical properties, and by measuring those differences across multiple probes, this system can determine exactly how much fuel there is, no matter how much the fuel shifts, sloshes and moves around. Obviously, at first glance, running electrical wires inside of the fuel tanks to power these probes would seem to violate the design philosophy of preventing ignition sources inside of the tanks, but this system was actually designed to be inherently safe. The idea was that even if an FQIS electrical fault were to occur leading to a spark, the energy available within the circuit would be too low to actually ignite the fuel vapor. The FQIS wiring was operating at extremely low voltage, only enough to discharge about 0.02 millijoules of energy, whilst the minimum energy theoretically needed to ignite jet fuel vapors is about 0.25 millijoules. So, in other words, over 12 times the energy carried in the FQIS wiring. Now, this seemed to be an elegant solution, but it had a catch. You see, it didn't eliminate the access of electrical energy, it only limited it. So, this safeguard only worked if the FQIS system was totally and completely isolated from any high voltage sources that were also present inside of the aircraft. That would mean insulating the wiring completely and also carefully separating it from other wiring in order to eliminate any risk of a short circuit that could create a path for high voltage currents to enter the tank. And on top of that, it would also be crucial to make sure that the integrity of those protections would remain intact for the entire lifespan of the aircraft. But within any airliner, miles of electrical wiring run through densely packed bundles, passing through various pressurized zones and equipment bays. And those bundles can contain circuits that carry vastly different energy levels, anything from these types of low power sensor signals to high energy electrical supply lines. Now, electrical energy will always seek to find the path of least resistance, and within the densely routed architecture of aircraft wiring, especially on these early 747s, the separation between circuits was maintained by insulation rather than distance alone. Now, although we can all see the inherent risks that would come with that approach, there was actually no FAA regulations at the time requiring the wiring for the FQIS or similar systems to be run separately from other types of wires. Instead, the aircraft manufacturers themselves had developed their own standards of separation. For example, McDonnell Douglas required FQIS wires to be separated from higher voltage wires by at least 3 inches, but Boeing had no such requirement. So, on many Boeing models, FQIS wiring was just bundled together with high voltage wires in multiple locations throughout the aircraft. And to make matters even worse, there were many factors that could increase the risk of short circuits occurring in the first place, and therefore allowing these type of energy jumps to happen between wires. For example, over time, insulation materials experience various kinds of mechanical and thermal stresses. Protective coatings age, chafe and crack, and bundles can be disturbed or moved during maintenance activity, repairs and system upgrades. Now, in many cases back then, that deterioration would then go unnoticed, since those wiring bundles were often located in places that were hard or even impossible for maintenance personnel to access. Also, back in the 90s, wiring inspections that were done were performed visually, with main emphasis on obvious damage. And that meant that less obvious issues like age-related degradation or contamination around the bundles could be overlooked even in the areas that were accessible to inspectors. So most likely because of these shortcomings, service difficulty reports filed with the FAA showed that electrical anomalies, intermittent faults and unexplained system behaviors were fairly common in aging aircraft back then. Later, after this story had unfolded, investigators would examine 26 in-service airliners of various types and ages in order to evaluate the condition of their wiring. And when they did that, they found that almost every aircraft, even those that were almost brand new, had some serious problems. Metal shavings that had likely been left behind during maintenance procedures were discovered within many wire bundles and connectors. Minor insulation damage was commonplace, and on several of the randomly selected aircraft in this study, investigators found evidence that wires had previously arced or even caught fire and melted together, only to self-extinguish without ever having been noticed. So you can probably see the problem here. If the fuel tanks contained flammable vapor, and the only protection against it igniting was the exclusion of ignition sources, but that wasn't actually being guaranteed, well then there wasn't really any assurance at all. And in fact, history had already demonstrated this. Back in 1990, a Philippine Airlines Boeing 737 had been sitting at the gate in Manila preparing for departure. All of its passengers had boarded and its systems were operating normally when suddenly an electrical fault developed inside of the aircraft's center fuel tank. Investigators believe that a damaged FQIS wire may have allowed electrical energy to travel into a faulty float switch, which then began arcing or overheating. Now, the center tank did contain some flammable fuel vapor at that time, so this arcing now most likely provided enough energy to ignite. The resulting explosion tore through the tank structure while the aircraft was pushing back from the gate, killing 8 passengers and injuring 82. So that accident alone had demonstrated the key vulnerability of the existing fuel tank design philosophy, namely that excluding all ignition sources 100% of the time was impossible. Fuel tanks are not immune environments. Instead, they are what we call managed environments, meaning that their safety doesn't depend on eliminating hazards entirely, but instead on carefully controlling the conditions under which those hazards could become dangerous. But by the time TWA Flight 800 took off from New York, that still wasn't being done properly. Back on board the 747, we now know that the center wing tank contained a flammable vapor mixture, at the same time as the aircraft electrical wiring carried the accumulated characteristics of decades in service, including insulation aging, routing proximity, and contamination. Now, none of those conditions alone guaranteed a catastrophe, but taken together, they now formed a system that was operating inside quite narrow margins, like the holes opening up in the Swiss cheese slices of Dr. Reason's famous risk model. And this is perhaps the most important distinction to understand about what was about to happen to Flight 800. It didn't come from an improbable chain of unlikely events, nor from a mysterious or unprecedented mechanism. No, it instead came from interactions of several underlying conditions that were individually quite common at the time. You see, for a number of different reasons, investigators would later conclude that the initiating event was almost certainly a short circuit involving wiring connected to the fuel quantity indicating system. Evidence of arcing was later discovered on high-power generator cables in the left wing, cables that had been bundled alongside FQIS wiring, interconnected with the center tank circuits. Additional arcing damage was also found on wires run through an area that had previously undergone structural repairs following a burst water tank, where maintenance activity had then disturbed existing wire bundles. Metal shavings were found within inches of where a missing wire bundle connecting center wing tank FQIS conductors would have been located, and that was also in a part of the aircraft associated with recent reports of water leaks, which could have created short circuits. In yet another area, center wing tank FQIS wiring had been co-routed with other high-energy wires who were supplying the upper deck flight attendant station with lighting. And that same wiring also shared bundle space with circuits connecting to the number 4 engine fuel flow indicator, as well as the cockpit voice recorder. Now, because a lot of wiring later wasn't recovered or was heavily damaged, investigators were never able to pinpoint the exact origin of the short circuit. Instead, they acknowledged that there might have been many places where it could have occurred, any of which might have allowed higher than intended electrical energy to enter wiring leading directly into the fuel tank. No matter what though, that energy should still have been unable to produce ignition given the design of the system. So this story now needed one last ingredient. Some type of mechanism capable of releasing that extra energy inside of the tank in the form of a spark. And that mechanism could very well have been something known as silver sulfide deposits. You see, cracks in wiring insulation can expose the conductors to chemicals around them, which can then react with the conductor itself to produce chemical compounds that subtly alter their electrical behavior. In this case, silver-plated copper wiring, which was common throughout this aircraft's electrical systems, had previously been found to react with the sulfur in jet fuel if conductors were ever exposed to that fuel within the tanks. This could then lead to depositing layers of silver sulfide contamination, which is a compound whose properties differ significantly from clean metallic conductors. You see, silver sulfide has semiconductive properties that reduce electrical resistance, which increases the risk of arcing between exposed conductors. And this type of contamination was something that usually went undetected during routine fuel tank inspections. Now, that silver sulfide contamination would reduce if the exposed conductors would be repeatedly soaked in more fuel, but since the center tank was filled up less often, any contaminants would grow worse there. In fact, inspections later revealed that silver sulfide deposits were common on FQIS wiring throughout the airliner fleet. But Boeing had not previously identified that as a serious safety issue. It was more seen as a nuisance that could cause erroneous fuel gauge readings. And the investigators would later come to believe that this silver sulfide was likely the last piece of the puzzle. The means by which an excessive current running through the FQIS wiring could start to arc, releasing enough energy to ignite the flammable fuel-air mixture inside of the tank like a spark plug. And so, with all of these factors in place, as this giant 747 kept flying into the darkening evening, somewhere within its huge electrical network, a short circuit now occurred. Like I said, the initiating wire was never found, but we know that it likely did happen at this point because the short circuit did leave some traces behind. As Flight 800 climbed through about 13,000 feet, the cockpit voice recorder captured two sudden drops in the background power noise, consistent with a power interruption on the circuit near the CVR wiring. Remember, this was run in the same bundle as the FQIS wiring. Now, like I mentioned before, that bundle also contained wires for high-power cabin lighting, as well as the wiring for the number 4 fuel flow indicator. Remember? That was the same one which the captain had seen showing crazy indications just a few seconds earlier. Most likely, this short circuit involved a higher power wire and an FQIS wire, which now transmitted a brief surge of electrical energy into the FQIS, far exceeding the low-energy design assumptions of that system. Before any circuit breakers had time to react, that voltage spike then traveled along unintended conductive routes and finally entered the center wing fuel tank. In the cockpit, this power surge now likely caused that strange fuel flow reading, but it also affected the fuel quantity reading for the center wing tank, causing it to spike to almost 4 times its actual value. But there would have been no time for the pilots to notice that, and even with that spike, the content indicated in the tank could still have been relatively small. Inside of the center wing tank though, those probes and sensors designed to measure fuel quantity now suddenly carried an amount of energy that they were never intended to hold. So in an environment already containing fuel vapor, heated to the perfect mixture by the air conditioning packs, the only thing needed for disaster was now the formation of an ignition source. And at time 20:31 and 12 seconds, it happened. A tiny arc, a momentary discharge, maybe released via a deposit of silver sulfide, now initiated a sequence of events that would be impossible to stop. The fuel vapor inside the center wing tank suddenly ignited, almost instantaneously creating an explosive overpressure event. Now, it didn't detonate in a huge explosion, as you might think. Instead, it created something known as a deflagration. That meant that a flame front now propagated throughout the tank at subsonic speeds instead of a shock wave traveling at the speed of sound. But even though this was slower than a full-blown explosion, it was still releasing the energy stored in the fuel so quickly that it almost immediately exceeded the structural integrity of the tank. And that also meant that inside of the cockpit, the crew had no time to diagnose, react, or even understand what was happening. You see, unlike a reinforced pressure vessel, the center wing tank is not just a hollow structure designed to hold fuel. No, it's fundamentally a structural cavity integrated directly into the wing box. The front and back walls of this tank are formed by major load-bearing structural elements, and several more load-bearing span-wise beams then cut through the space inside of the tank as well, all of which were critical for the structural integrity of the entire aircraft around it. So as this overpressure event now quickly unfolded, a span-wise beam running across the tank soon separated with tremendous force and then toppled forward into the front spar, which is a key structural beam that also forms the forward wall of the tank. As the pressure wave then moved forward, the front spar tumbled forward and struck the nearly full potable water tanks located directly in front of it, crushing those and simultaneously fracturing the spar itself, which dramatically reduced the spar's rigidity. And without that rigidity, it was then unable to support the fuselage skin below it, which immediately began to buckle. Now, aircraft skin, although engineered to remarkable strength in order to withstand the loads from pressurization, derives much of that load-carrying capacity from the structural parts attached to it. So with the front spar no longer functioning as a stiff support, the lower fuselage skin directly below now became vulnerable to the still expanding pressure forces generated inside of the fuel tank, and it therefore tore open into a big gaping hole. That caused the damage to cascade further, because with the fuselage skin now gone and therefore not longer able to hold the forces from the pressurization in the cabin, the structural parts surrounding the hole were now subjected to downward loads that they were never designed to carry. Under that stress, components directly above the hole fractured and then fell out, and that included spanwise beam number 3, portions of the front spar, as well as a section of the critical keel beam. The keel beam runs along the entire length of the aircraft and functions as its structural spine, giving the entire airframe its longitudinal rigidity. So when it fractured, it was a fatal event for the structural integrity of the entire aircraft. With its spine now compromised, it could no longer sustain the bending loads it was normally subjected to, so the aerodynamic forces that were acting upon it now redistributed catastrophically, with the fuselage skin tearing all the way up and over the top of the upper deck, essentially splitting the aircraft into 2 pieces. The forward section, which included the cockpit, immediately ripped away and began falling down towards the ocean. And what's important to understand here is that the time that it took from that initial spark in the tank to the entire nose section falling away was just 3 to 5 seconds, which is less time than it took me to say this sentence. Now, what makes this sequence particularly important is not only the mechanics of the breakup, but also how the investigators were later able to determine how it had happened with extraordinary confidence. When the wreckage was eventually recovered and reconstructed, investigators observed clear signatures that could only have been the result of a fuel tank explosion inside of the center wing tank. Metal skin was found to peel away from the tank surfaces rather than inward. Structural elements left witness marks where they had collided during the breakup, and soot and carbon deposits were distributed along internal surfaces in ways consistent with the combustion happening inside of the tank. Now, these findings matter a lot, because they show evidence that differs fundamentally from what would have been shown if this accident had been caused by external blast sources or high explosive detonations. And equally important to what the investigators found was what they didn't find. Despite detailed chemical analysis and forensic examinations, no evidence of high explosive residue was ever found on any of the victims inside of the aircraft. No high explosive shrapnel patterns were present, and no fragments consistent with an explosive device were ever recovered. A bomb detonation leaves telltale micro-pitting and discoloration of adjacent metal, as well as residues concentrated on nearby components, none of which were found in any big quantities on the recovered wreckage. Now, there were a few small traces of explosive residue found on individual pieces from a couple of different non-connected locations on the aircraft, but since it was so little and not found in a consistent pattern, this was later discarded as likely being transferred from one of the military vessels that took part in the recovery effort. So together, all of the physical evidence eventually eliminated the possibility of an external explosive device, not through assumption, but through mechanics. Anyway, with the entire nose section now missing, the mangled Boeing 747 had now suddenly been transformed from a carefully balanced flying machine into something that was aerodynamically deeply unsound. You see, planes are made aerodynamically stable by a carefully coordinated interplay between the wing's horizontal stabilizer and the center of gravity. So, when this explosion removed 80,000 pounds of structure from the front of the aircraft, that pitch balance instantly collapsed, and the seesaw tripped backwards as the plane suddenly became tail-heavy. With the wings continuing to generate lift, the tail continuing to generate downforce, and the engines probably continuing to generate some thrust, a powerful nose-up pitch movement now occurred, driven purely by the geometry of forces acting on the airframe. That nose-up moment, the reduction in weight and the fact that the plane was already climbing when it exploded, caused what was left of the 747 to continue climbing even steeper. And at the same time, the now blunt open end of the fuselage started generating enormous amounts of drag, which quickly slowed the airframe towards its stall speed. In fact, radar data analysis, computer simulations and reverse ballistic analysis showed that the remaining part of the aircraft most likely climbed between 2,000 and 3,000 feet as its forward kinetic energy was converted into altitude. Then eventually it reached nearly 16,000 feet before it stalled, rolled right and then entered into a nearly vertical descent down towards the sea below. And it is really important to note that it was this moment that has caused so much confusion in the aftermath of the accident and has contributed to the misinformation that persists even to this day. You see, the rear two-thirds of the fuselage was still spewing burning fuel into the darkening sky as it climbed upwards during the last couple of seconds before it stalled. And this fire was likely visible for dozens of kilometers. As a result, hundreds, if not thousands of people witnessed at least some portion of this accident sequence, and many of them to this day believe that what they saw was a missile hitting TWA Flight 800. Most of them reported seeing a streak of light shooting upwards before exploding, which, if you don't know all of the facts here, sounds a lot like a missile hitting its target. But that is what Hollywood movies has told us that a missile strike looks like, not what it actually looks like. Real missiles shoot off the ground with incredible speed, burning their motors hard for a few seconds and then become nearly invisible for most of their flight as they coast on their momentum. Because of this, witnesses to a real missile strike would never see a streak of light hitting the plane, just a streak near the ground for a few seconds, followed by an explosion in a totally different location as the coasting missile hits its target. And nothing like that was seen in this area on that night. On top of this, there was, like I mentioned before, no physical evidence of a missile strike, like widespread peppering of the fuselage by high-energy fragments, which is what we have clearly seen on planes that have actually been hit by missiles, like Malaysia Airlines flight MH17 or the Azerbaijan Airlines flight that was hit back in 2024. So instead, as I already said, all of the physical damage pointed to an overpressure event in the center fuel tank and nothing else. But what was that streak of light that the people were seeing then? Well, as you have probably guessed by now, that was likely just the burning aft part of the aircraft as it was continuing to climb after the initial breakup. When it then stalled and started accelerating almost vertically downwards, the aerodynamic loads increased dramatically, which accelerated the breakup further. The wings soon broke away, with their fuel tanks releasing most of their remaining fuel into the fiery inferno that it left behind, and that was likely the final explosion that was seen by most witnesses. So the way that this would have looked like would have been a small light climbing upwards, then followed by a big explosion. The tail then also separated, and what was left of the disintegrating wreckage plunged burning down into the Atlantic Ocean. About 50 seconds after that initial explosion, all of the pieces had finally rained down, completing the destruction from that catastrophic event that had been initiated thousands of feet above. All 230 people were killed, either by the initial breakup or by that final impact with the ocean. Now, what followed this tragedy was an investigation of extraordinary scale, and one that would ultimately become one of the most meticulous technical examinations ever undertaken by the National Transportation Safety Board. Recovery vessels, divers, remotely operated vehicles and sonar mapping systems were deployed across a vast area of the Atlantic seabed, where investigators then worked for months to locate, identify and retrieve all of the wreckage scattered by both the breakup sequence and strong ocean currents. Piece by piece, fragment by fragment, the remains of the aircraft were then lifted from the ocean floor until remarkably almost 98% of the airplane had been recovered. And what made this effort so impressive was not only the quantity of debris recovered, but what the investigators chose to do with it. Inside of a hangar, the aircraft was eventually reconstructed in skeletal form, with its fuselage contours carefully reassembled from thousands of recovered components and its internal structures mapped, aligned and studied. Deformation patterns, fracture surfaces, soot deposits, wiring remnants, structural separations and burn signatures could now be examined in their spatial relationships, allowing investigators to trace loads, pressures and failure paths with a level of clarity that was required to explain how an airliner had simply exploded in mid-flight. Every plausible hypothesis required evaluation against physical evidence, aerodynamic modeling and structural mechanics. So by the time that the final report was published, nearly 4 years later, the investigation had grown into one of the most exhaustive in NTSB history, both in scope and in scientific depth. But the lasting importance of Flight 800 doesn't come from how the investigators came to their conclusions, but instead in the way that the aviation industry learned from it. This accident fundamentally altered the understanding of fuel tank safety by demonstrating that it couldn't be assured by preclusion of ignition sources alone. And in response, regulators mandated the development and installation of fuel tank inerting systems, technologies designed to pump nitrogen into empty fuel tanks to prevent the development of flammable fuel-air mixtures, and by around 2018 or so, virtually all airliners were fitted with these new systems. At the same time, this investigation accelerated sweeping changes in wiring inspection philosophy, maintenance practices and certification standards, and it clearly showed that electrical systems, unlike many structural components, could degrade invisibly but still pose a threat of producing catastrophic consequences. Wiring, insulation, connectors, possible short-circuit paths, contamination environments and latent electrical vulnerabilities therefore became central elements of long-term airworthiness thinking. So this accident didn't reveal a single hidden defect, but instead illuminated how ordinary, widely distributed conditions could interact to reduce safety margins. TWA Flight 800 remains a profoundly tragic event, but it also stands as a great example of how aviation learns from relentless examination of each failure. So in that regard, this accident is probably one of the best examples of how an accident can lead to changes that continues to shape how modern airplanes are built, inspected and protected from the risks that once went unseen. Now, over on our sister channel, Mentour Now, we actually did a video about the problems that the new Air Force Ones are having, much of which can be traced directly back to this accident and the new regulations around cable separation that it brought. Please make sure that you have subscribed to both of our channels if you want to see more content like this, and if you want to get more deep diving industry explanations connected to it. My name is Peter Hörnfeldt and you're watching Mentor Pilot. Have an absolutely fantastic day and I'll see you next time. Bye bye.